So, welcome back to our video lectures on projective geometry. We are still in our chapter about projective calculations, where we want to tighten the gap between geometry and algebra in a very specific way, and this time we will deal with so-called von Staudt constructions, which play a really crucial role there. So von Staudt constructions were first introduced by a mathematician named von Staudt, and he was one of, I would say, the really great geometers of the 19th century. One has to say that he was not extremely extrovert, so his work is, I would say, in a certain sense, very silent, but its influence cannot be underestimated. It's really a milestone in projective geometry, what he did. So what he did, he wrote a series of articles and a book called Geometrie der Lage, so geometry of position, and in that book he, somehow made an approach to projective geometry that frees it from being defined over certain coordinates fields, while still be able to do calculations in these geometries. And over the next 3 video lectures we will go along that path, and what we first need is what is today known as so-called von Staudt constructions. Here I've copied 2 more or less random pages of the book, the introductory, the first page here and one of the later pages, and you may recognize, and this is really representative for the whole book, that it just consists of text. So von Staudt had the habit to write his book in a way that they only contained texts and neither pictures nor formulas. And I cannot resist quoting Lewis Carroll and the first paragraph of his beautiful Alice in Wonderland book here, where Alice asks, and what is the use of a book, thought Alice, without pictures or conversations? And as a mathematician I can add, and even without formulas. And well, the question is, what is the use of that book? It changed projective geometry. So it put projective geometry on a basis such that it equally stands with the numbers of a field. So let me just quote from a Wikipedia article about Christian von Staudt. The book Geometrie der Lage was a landmark in projective geometry. Staudt was the first to adopt a fully rigorous approach. Without exception, his predecessors still spoke of distances, perpendiculars, angles, and other entities that play no role in projective geometry. So, what did von Staudt do? He gave an approach to projective geometry that does not rely on underlying notions of distance, coordinates, and. He constructed that intrinsically coming from the field itself. And if you look closely what we did so far, we did geometry, we first defined our axioms A1 up to A3, but we at some point found out, they are not rich enough, because we cannot really do nice incidence theorems over these just 3 axioms. We need something more, and then we went on and defined projective geometry over a field. But as soon as we define projective geometry over a field, we introduce coordinates, and as soon as we do calculations with coordinates, we do intrinsically measurements. So essentially, we based our point of view of projective geometry on a kind of already existing measurement theory. And what we are going to do in the course of this and the next 2 video lectures is we will free projective geometry from the underlying field in a certain sense. So what have we done so far? So we started essentially by taking our four axioms, but one step further, we always said we start with a field, and from that field we can construct a projective geometry. And so what I showed you, for instance, was that if we do that, then certain incidence theorems, like theorems of Pappos and Desargues, hold within that geometry. But if you remember the proofs that we did for Pappos and Desargues, they relied on calculations. And being well dependent on calculations means that we somehow depended on the field. Another thing we did, I introduced cross ratios. So they were in invariant properties or invariant measures in projective spaces. So they helped us to get from a set of points to a certain numbers. And again, we had to do that by doing calculations. So again, we relied on our field. And then I gave you the notion of quadrilateral sets. That was a nice geometric property. To check this property, we had two possibilities, and that was one of the really important things that we did in one of our last lectures. We could either do the calculations, check whether a certain equation holds, or we could do a geometric construction. So in a very concrete sense, the quad sets related the algebraic theory of having a certain equation to the geometric theory of having a certain construction. So in a certain sense, these quad sets somehow formed a link between geometry and algebra. And now we will further work out that link and strengthen it to such an extent that at the end, on that link, we can base an independent formulation of projective geometry. So what do the von Staudt construction do? They really model addition and multiplication. So they are geometric constructions that really form a link from geometry to algebraic concepts like addition and multiplications. So the von Staudt constructions are only a tiny part of von Staudt's theory. We will see a bigger extent of his theory later on, but in this lecture we will focus on these so-called von Staudt constructions. And there are three ways to approach them. One of them is geometrically, the other is algebraically, and we just have seen they form a link from one field to the other, and the third way of viewing them is from an axiomatic point of view. And let me just give you a few pictures and formulas here. So the so-called von Staudt constructions are nothing more than those two really innocent looking pictures I'm showing you on that page, and they are able to model addition and multiplication. So essentially what we will see, that if you have a line that you consider to be a line for calculation, and you put a 0 here and a point x and a point y here, this point here plays the role of x plus y. I will explain in a minute what I exactly mean by that. And similarly, this point here plays the role of x times y. So let me switch to the algebraic viewpoint. It turns out that these constructions that you did here, this one and this one, are nothing else as certain quadrilateral set constructions. So from a different point of view, you could also think about quad-set constructions. Now comes the axiomatic point of view, which is a kind of quantum leap in thinking at that point. The idea is to just take what we have here as a kind of inspiration to define addition and multiplication in a purely geometric term, and by that discover a field structure within projective geometry. So let us now first focus on the von Staudt construction, and let me start very, very elementary. So I give you a task. So here's the task. Say I give you a kind of measuring device, and I give you two lengths, two sticks essentially, a blue stick and red stick, and I ask you, well, if those sticks have two certain lengths, for instance the length 2 and the length 3, how would you construct a stick of length 2 plus 3, so a stick of length 5, just from those two sticks here? So I ask for the position of 2 points whose distance is the sum of the two lengths. So, well, the first task is really simple. So you just have to put one stick after the other, and then you get an entire length that is the sum of the two, because, well, addition is modeled in a way such that it models the well, consecutive joining of lengths. So this is somehow a very intrinsic situation for addition. How about multiplication? I give you two lengths again, say 2 and 3, and I ask you to construct a stick of length 2 times 3 just from the measures that I gave you here. Your first idea might be to say, well, my first, well, analogy that comes in my mind for multiplication is to form a rectangle, and this rectangle has area 6, so I essentially solved the problem. But as a matter of fact, you didn't, because this here is an area and not a stick length, and so you have to find some other way. So doing with areas doesn't work, at least not at first sight. So what else can we do? Actually, we can use proportional relations. So, and for that I have to introduce one more stick into the game, a stick that plays the role of the unit length, the distance between 1 and 2, between 0 and 1, and the distance between 0 and 1. And now I form the following figure. I form a little triangle with side lengths coming from one of my sticks and the one. And then I make a second copy of that picture, which is just blown up by a certain scaling factor, such that you get a similar figure to that with the length 3 at that side here. And if you do so, you can really calculate and see that this length here has to be exactly the product of those two. So what you essentially get here is you have a length 1 here and a length 2 here, and this is the same as comparing a length 3 to a length 6. So the equality of those two fractions helps you to construct that stick. So we still measured, we still did very, very elementary constructions. Now I give you the following task. Do the same thing in projective geometry. So now I tighten your hands and ask you, well, you are only allowed to use constructions that involve points, lines, and incidences, and do the same kind of well, mimicking addition and multiplication here. I give us a little bit convenience device. So in the projective plane, we may single out one line and say, well, this one line should play the role of the line at infinity. And if we do so, then we can define parallelism with respect to that line. And you see parallels play somehow a role in that picture here. So I also allow singling out a line at infinity and talking about parallels. This will make our pictures way simpler than if we do the fully general case. So here is the von Staudt constructions. So if you look at those two pictures, lines that seem to be parallel should really be parallel. So let me first explain you how these pictures have to be read. So assume you have a point 0, a point x, and a point y, and given on this yellow line, then behind that picture there is a certain construction. So the construction goes as follows. First, choose a line that is parallel to the other line, the blue line up there, here, and then on that line choose an arbitrary auxiliary point, the red point here. From that point, draw two lines connected to your two green points. And now do the following construction. Take the point at y and construct a parallel to that point, through that point, to this line here, and intersect it with the blue line up here. And from there, draw a parallel to the other line, and you will end up at a point with coordinates x plus y. So if you don't believe it here, I have some concrete numbers taken from my drawing here. So this point here is placed at 1.5, this point here is placed at 4.5, and you see this point here is placed at 0.6. And the essential idea is, with that construction, you have copied this triangle to that position, and by that copied this length from here to here, which corresponds to placing behind each other two sticks. So multiplication is a little bit more elaborate. Just as a first check here, again, lines that seem to be parallel are assumed really to be parallel. So what you do here, you start with points 0, 1, then x and y, and you calculate or construct the point 6 by first saying, well, I have this line, take an auxiliary point, draw these two lines here, then I draw a parallel from here to here and a parallel from here to here, and I end up at a point which should be the product. And why does this work? So let me give you some explanation. So first of all, above here, I just marked those two triangles. They are identical figures, and the whole construction is based on the fact that those two things are identical. Here we have to do with similarities, and if you stare a while at that picture, you may recognize that this small figure I've drawn here, consisting of the pink and the blue triangle here, is just a small scaled copy of this big picture that you see here, consisting of this triangle and this triangle. And so, since these two pictures are essentially similar, you get exactly what I told you about the proportions of stick lengths. You see that essentially 1/2 is the same as 3/6, which gives you the construction here for 0.6. So let us go one step further, and next thing we should observe is that these von Staudt constructions are in essence quadrilateral set relations. So how do we recover quadrilateral set relations in our drawing here? Well, I said we include parallels, so by including parallels we somehow moved our line at infinity far out, and now let's move this line at infinity again back into our picture, and I first do that diagrammatically. So we saw these two lines here are parallel, though they will meet in some point that lies very far out. Also, these two lines here are parallel, though they again will meet at a point, and these two lines are parallel as well, so also they will meet at a point. So I get on the line at infinity those 3 points here, and I know my line at infinity must go through those 3 points, and with very good reason I can label that point here to be the infinite point on our yellow line. But now look what we got. So the whole construction consists of one line with some green points on it and 4 points, and between those 4 points we have drawn all possible connection lines and intersected them with the yellow line. So essentially what we did here is a construction of a quadrilateral set with, in that case, 2 coinciding points. Let's look at multiplication. Again, these 2 things are parallel and these 2 things are parallel, so they meet in a point and they meet in a point. These 2 points lie on the line at infinity, so if we take the line at infinity, the unique line through these 2 points, it intersects our yellow line here at one point, and we can give that point, with good justice, the label infinity. And again, we have construction of 6 green points on the green line that arise from having 4 points, all possible connecting lines, and the 6 intersections. So again, we have a quadrilateral set. So take home message, in both cases we can recover the von Staudt constructions as quadrilateral sets. So now I want to start to look things from a kind of upside down manner, and let me first recall, you should remember the quadrilateral sets were a relation between points that was projectively invariant. So I can move my points, not all points, but the projective basis to any other position. With them go x, y, and the product and the sum of the 2 points, and the quartet relations will still remain the same. So we can now, well, we already, by geometric reasoning, proved that von Staudt constructions do this kind of addition, but now we want to do this purely algebraically by using the quadrilateral set relation and using it at some position in the standard embedding. So now consider the following. Assume that our points here are points given in the standard embedding, that the blue letters that we have here are essentially labels for the points, and we gave them corresponding coordinates in the standard embedding. So being a quadset up there means, so let's assume all that happens in the one-dimensional projective line. This means that certain 2 by 2 determinants, the product of 3 of them, have to be equal to a different product of 3 2 by 2 determinants. And if we are in the standard embedding, then we can say, well, take the standard coordinate for those points. So the point infinity has a 0 in the last spot and has a 1 in the first spot. The point y, we place him at the position that corresponds to y on the standard embedding. So this would be y1, x would become x1, x plus y, which is at that point here still just the label for the point, should be placed as at position x plus y, and so on and so on. So, and now we can do the following. We can check if this equation here is actually a proper equation, whether it's true. So let's just check. So we get this determinant here results to be 1. This here is x minus x plus y. This here is minus y. this here is a 1. Now I think I confused those two terms. This determinant here is this minus x, and this determinant here is this minus 1. And if you look at this equation, you immediately see, well, these two x's here simply cancel out, and what I have is minus y on, no, plus y on this side and plus y on the other side, which gives you a true equation. Let me interpret what I just did. So what we got here tells us, in the standard embedding, this here is a true equation. So if we place infinity y x 0 at the positions in the standard embedding where they encode the corresponding points, and if we have a quadrilateral set relation to this point here written as x plus y, then this point x plus y will be at a position that is at x plus y. Please meditate about that because it involves some kind of brain twister to really think of these points that I have here as just as labels of points that have been placed at the right position. The same thing happens for multiplication. So here I again have a certain quad-set relation. I have this product of determinant equals product of determinant. I put everything into the standard embedding. I write down the corresponding determinants. Let me just check. So this determinant here gives a minus x. This here gives x minus x times y. This here gives a minus 1. This here gives x times y, but with a minus. This here gives a minus 1. And this here gives a 1 minus x. And if you well evaluate left and right side, they will simply coincide. So the same thing happens for multiplication. So again we can say, if in standard embedding we place 0, 1, infinity, x and y at positions where they play the roles induced by, well, the corresponding numbers, then if we have this quad-set relation here, then automatically our point x, y will be at the position of x and y. Let me now, in the next step, free us from the certain position of our points x and y, and really, not x and y, the certain position of our projective basis. So, and in these pictures, I moved our point at infinity to a projectively finite position, and here you see now really with straight line constructions the two quadrilateral sets. And now we will in the next step see that the entire idea still makes sense with respect to an arbitrary projective basis on the line. So what we do, we start with a field, we take the corresponding projective plane over that field, then in the projective plane we single out one line. This will be our yellow line, and on that line we fix 3 points 0, 1 at infinity at arbitrary positions. The only rule that we need is that they do not coincide. I told you in the lectures about the cross ratio that if we do that, and if we consider the line to be essentially a copy of the one-dimensional projective line, then the cross ratio defines a bijection between points on the line and numbers in K union our one special point, the infinite point. So whenever we take a point on that line, we can calculate the cross ratio. These are again field calculations, and get a number, and this is a bijection. And this is a bijection we get through that projective scale. So essentially, if you have something like 0 here and 1 here and infinity here. So the other numbers get somehow, the 2 becomes a place here, 3, and they get closer and closer and closer. And we get those projective scales. Please remember the railroad tracks. So now after we did that, and after we have this isomorphism, we now do the following. I take arbitrary 2 other points P and Q on L. They could even coincide with 1 or 0, and I define the point P plus Q as the unique point on L that satisfies this quartet relation. And I define P times Q to be the unique point on L that satisfies this quartet relation. And if I do, though, by everything we said so far, we will get the following nice functional equations. So if you take your 2 points and well, you first translate their positions into numbers by our function phi, and then add these 2 numbers, you will get a number that is the same as if you first constructed your addition point and then translated it to a number. So you have kind of homomorphism between things that happen on the line and things that happen with your numbers. And the same happens for multiplication. It doesn't matter if you first translate your points into numbers and then multiply, or if you construct the multiplied point and then translate it into numbers. You may ask for a proof for that, and actually we already did the proof. You just have to put the pieces together. So what we actually did is we considered L to be a copy of the that R here should perhaps be a K. So we are over any field. It should be a copy of K pi 1. And what we proved, that these 2 functional equations work if we are in the standard embedding. These were the last 3 slides. But now we know that both the cross ratio and the quadrilateral set relations are invariant under projective transformation. So with proving it for the standard embedding, we automatically proved it for the general case because everything is projectively invariant. Please press the stop button here and contemplate over that slide and take all the logical steps that are necessary to make that work. Look at the interplays of quadsets, von Staudt constructions, the bijection we have, projective invariant, because everything comes together in this one slide. Let me finish with a few concrete examples. So here I've really done the construction. So we have a point 0, a point 1, and a point at infinity. And here I've constructed the projective scale just to see that this is really free construction. Let me move my points at infinity, 1 and 0. And up here I have encoded the von Staudt construction for addition, and let me just show you that everything works as I claim that it works. And for that I move my point 2 here to some specific coordinate. Let's take the example of 2 and 4, and what you see here is that indeed 2 plus 4 ends up at a position 6, even in an arbitrary projective scale. So a few more examples. Here you see, for instance, 2 plus 6 is 8. Or let's do one more. Let's take 4 plus 4 is 8 as well. So you see it works nicely for arbitrary choices of p's and q's. Same thing for the multiplication. Again, we have a projective scale that can be chosen completely freely, and I now adjust my x and y to resemble certain multiplication tasks. So let's calculate 2 times 3, and what we really get here is a 6 by just doing this nice little geometric construction here. A few more examples. 2 times 4 turns out to be 8, and 4 times 4 turns out to be too large for my examples here. So let's do one more. Let's take 3 times 3 is a nice 9. So you see, you can also nicely square with these kind of constructions. Let me take that a little step further and show you the power behind those von Staudt constructions. Look at the following example. So I may ask you to construct a configuration with those, it's altogether 8 plus 5, it's 13 points, such that all collinearities you see in that picture are indeed satisfied. But look what I've done in that picture. I've constructed an addition here that forces the intersection of this line and the yellow line to be at position 2. And here I constructed a multiplication device that forces the square of that point to be at 2 as well. So the position of that point must be a number that multiplied by itself gives 2. So the only two positions for that point can be square root of 2 and minus square root of 2. So by using von Staudt constructions, I encoded square roots into geometric constructions. You can even go further and say, give me your favorite algebraic number. Algebraic numbers are defined to be the roots of polynomials. Encode the polynomial into von Staudt constructions, and I give you a configuration that it requires your algebraic number to occur in the coordinates if you want to get realization. So for instance, you could construct something that requires a number x with the property that x squares equals minus 1. If you do that construction, you end up with a configuration that needs something like the complex numbers to be realizable. So far, for the moment, with von Staudt constructions, we will see that they form the key to really discover a field structure in projective geometry. But before we do so, we have to once more get back to incidence configurations, and we will do so in our next video lecture.